So I've seen quite a few people struggling with Statistics 201, 210, Chapter 4. So I decided to make a video going into depth on how everything works and how everything is derived. Now, the slides themselves, they only state the facts. They don't state the actual details that you need. And if you watch the lectures, you're going to spend 10 hours trying to understand everything. So I decided to make a video just summarizing everything that's going over everything that's going on and deriving most of the equations till the distributions at least. So however, I'm going to go quite into depth in this video, deriving all the equations and such. So if that's not what you're looking for, you might not want to watch the video. So discrete random variables and distributions. So the first thing that you should encounter is this formula over here, which is just the sum of the frequencies is equal to 1. Now all this is saying is that if you have all the possible things that could happen, the possible events that could happen, then each event will have like a certain frequency out of that total. So maybe this is the frequency of one event and this is the frequency of another. However, in the end, if you add up all these frequencies, then if you add up all the numbers, all the probabilities of each event in x, then you would get 1. Therefore, whenever you see this equation, just think the sum of the frequencies, this is the total probability, which is going to be equal to 1. So the most frequent formula that you're going to see in this chapter is going to be E of x. Now all this is the mean of x, so the average of all values. So if you're confused about how this is the average, you could take an example. So if you had a few numbers like 1, 2, 3, how would you get the average of these three numbers? So what you would do is that you would add 1 plus 2 plus 3, then divide it by 3. And then the average would be 6 divided by 3, which is going to be 2. However, there's an alternative way. So instead, you could get the probability of each one. So this is x, this is f of x, or the probability of x. So this is going to be 1 over 3, 1 over 3, 1 over 3, and it would result in the same equation. And if you add this all up, you would get 2. And as you could see, this is just the sum of x times f of x, or the probability of x. So to get the mean, all you do is get the sum of x, the value, times the probability of that value. Now, this formula isn't simply just for the mean, but you could apply it to a lot more stuff. So instead of just passing in x to E of x, which would result in sum of x times f of x, you could pass in something else, such as e, then the value e, tx, and you're going to see this later on, the moment generating function. So that would be x etx times f of x. Now as you could see, while over here you did x times f of x, now over here all you do is that you change x to be e t of x. And if you look at this part in the slide, so e g of x is going to be equal to the sum of g of x times f of x. Now if you don't understand this formula, I would recommend you to try understanding it until you move on in the rest of the rest of the chapter, because everything else relies on this formula and relies on passing in other formulas into this. So passing in g of x into here, you would get that. So a good example of passing in a function into this is just passing in ex squared, and that would result in the sum of x squared times f of x. And if we go back to this example, all we do here is we square all the numbers. So 1 squared times the probability of getting 1, 2 squared times probability of getting 2, 3 squared times probability of getting 3. And this is called the second moment. Now, in my opinion, moment, it's just a name or like an abstraction for just saying e to the power x to the power r. So when you say first moment, all you're saying is x to the power 1, and this would be the mean of x. However, if you pass in e of x squared, then all you would do is change this, the power of this, and f of x stays the same, and that applies to everything else in the chapter. F of x always stays exactly the same. So what if we pass in x to the power 0? So then it would be, this would be 1, and the sum of f of x, as we said, is just going to be 1. So you could say e of x 0, and this would also be 1, and this would be 1. So expected value of 1 is just going to be the sum of the frequencies, which is going to be 1. So if we say expected value of k, then it would be the same thing as k times x to the power 0. So sum k times x to the power 0, which is 1, times f of x. Now when you have a sum, you could just move a constant outside. So the sum of f of x is going to be 1, so 1 times k. So the expected value of a constant will be the constant. It won't change. That's because the sum of f of x is going to be 1. Now if you do, so we talked about the moments. So second moment is going to be the average value of x squared, and the first moment, which is e to the power x, is going to be the average value of x, and e to the power 1 is going to be just 1, the sum of the frequencies. Okay, now for some properties of the mean. As we said here, e of x is the average value of x, or the mean. They're interchangeable. All three are interchangeable, as far as I know, at least. So as we see here, e of k will just result in k, and we could do the same thing with e x plus k, which would just be the sum of x plus k times f of x. And if you expand this, it would just be x f of x plus the sum of k times f of x. So instead of saying this, we could also say ex plus ek. And as you could see over here, the e of k is just going to be k, because the sum of f of x, if we move this outside, is just going to be 1. Some of the probabilities, my bad. And if we do e 2 times x, so now let me emphasize on what this means. So if you had a distribution of x, so these are all values of x. Let me just draw the axis. So let's say that this is a distribution x. Now if you make a new distribution, which is y, and then you add k to it, then all you would do is, so this is the original mean. So when you apply this, I think, transformation, I'm not sure the exact terms, but all you do is that you shift the distribution by k. Like you shift every single value of x by k. So this would be, let's say, 5. Then this would be 5 plus k. And then you just draw the same distribution, but it's shifted by k. And when you move every single value by k, then the mean will also be shifted by k. I hope that makes sense, and if it doesn't, try thinking through it, because this concept, when thinking like this, would help when deriving the variance stuff. So what if you doubled every value of x? So from the same example, as you could see over here, n plus k, and over here this is the mean. So let's say that this is the mean of y. So the mean of y is going to be equal to the mean of x plus k when you add a constant to it. Now let's talk about multiplying a constant. So when you multiply a constant to every value of x, so let's say that instead of x plus k, it's going to be 2 times x. So let's take actual values, so it would be easier to understand. So let's say that this is 2, and let's say that this is 3, and this is 4. And let's just expand this. So 5, 6, 7, 8. So let's double every single value of x, as we said over here. These are all the values of x. So now let's double it. And this is just an example. I'm not sure if that would actually be right, the shape of the distribution, but just take it as an example. So 2 times 2, it's going to be 4. 3 times 2 is going to be 6. 4 times 2 is going to be 8. So what we're doing is that we're doubling. So horrible. So what we're doing is that we're doubling every single value of x. So if it was x over here, it would be 2x over here. And as a result, if the mean of x is 3, this is going to be y, the new thing. So the mean of y is going to be equal to 6. So as you could see, if you do e 2x, that's the same as 2 times e to the power e of x. Now this is like a logical way of doing it. However, there's also, as I showed you here, there's a mathematical way of doing it as well, but it's easier to understand the logical way. So if you want to try doing this, it would be the sum of 2x times f of x, and all you could do is just move the constant outside the sum, so 2 times x f of x, which would this is just e of x, so it would result in the same thing. So let's say that y is equal to 2x, so the mean of y is going to be equal to 2 times the mean of x. Okay, now on to the variance. Now, a good question is, what is the variance? Most people, they do not know what the variance is, and if you understand it, it would be much easier to handle this concept, this chapter. So this is the mean of y. So over here, this is a certain distance, and what the variance is the average distance squared from the mean. So let's say that, okay, average e E gives the average. It takes a function and gets the average of that function. So the average distance from the mean, x minus m squared. Now I think the origins of this formula is, so standard deviation is just the square root. Standard deviation is the square root of the variance. So I think the origin of this, a very close formula to this, is, I need to draw the distribution for you to understand it, but let's say that this is a distribution and this is the mean. Now if we get the average distance, okay, let's say that, let's put actual values. So let's say this is 5, this is 10, this is negative 5, this is, let's say 0. Then the distance here, so let's calculate this distance. So it's going to be 10 minus 5. But now we want to use the same formula for this side. So it's going to be 0 minus 5. And this is going to give you negative 5 and 5. However, distances, they do not have the, at least like scalar distance, they don't discriminate between positive and negative distances. So what you would do is you would remove the negative part. So how would you remove the negative part? You would square it. So when you square it, it would become negative 1 squared times 5 squared. But now this value is useless. How would you use 5 squared? Now you remove this, okay, it's going to be 1. But now this value isn't the original average distance that you want. So what you do is that you would square root it again. So the average distance from the mean is going to be x minus mean squared times f of x. Now you could probably see some similarity with this. So this is just e of square root x minus m squared. However, the variance is e x, oh, this is inside the parenthesis. So the variance is e x minus m squared. Now as you can see, like there's a similarity between these formulas, right? However, there is one small difference. Over here, when you're calculating the standard deviation, you get the square root of everything, the square root of the sum, so on the outside, not in the inside. So over here, it's going to be the square root of the variance, which is this formula here. So as you can see, there's some properties changing. So to recap, standard deviation is very close to the average distance from the mean. So if we get this, okay, average distance, okay, we don't want negative values, so we square it, and so distance squared, then square root, okay, that removes the negative value. However, if we have an, I'm not exactly sure of this, but my suspicion is that if you have like outliers or like extreme values, then the standard deviation would be sensitive to them, as the distance would be squared, and you would get the difference between, so the further away it is from the mean, the more the distance is affected, and this is not equal to this. Where is it? Yeah, these two formulas, they're not the same. So there's a small difference. So now I hope that you agree that the variance is simply the average distance squared from the mean. And to do that, okay, the average distance from the mean, to recap, it's just x minus mean squared. and that's all the variance is. So the standard deviation is just the square root of the variance. Now you probably don't need to memorize that, but this formula is going to be useful for later on when we look at the properties of a variance. So as I said before, if you have e of x, that would be the mean. And if you have e and you add you multiply a constant to x, and then you add a constant, then it would be 2, this is mean of x, so you could say that this is y. If you so you could say that this is y. So let's say that you have a new mean called mean of y, and that's going to be a times the mean of x plus b. So as I said, recap, this is the mean. You're multiplying every single value by 2 and you're adding b. So it would create like a new distribution. So to create a new distribution that has that's just like transformed from x to y. I'm not sure if transform is a correct word, but I hope you get the idea. So if you have e of x, that would be the mean of x. Now if you add a constant and you multiply the constant, then it would result in the same thing in the mean in terms of x. So now let's go to the properties of a variance. So var x is the same as expected value. As I said, the expected value formula is very important. So the expected value of x, the average of the x, of the distance between the mean, x and the mean, squared. And now if we add, so this is going to be variance of x. So now if we have like a function y, and then we add a constant to it. So let's find the variance of y. So that's going to be e. Now all the values of x are shifted by k. So it's going to be x plus k. Then minus. Now as we said before, when you add a constant to the mean, when you add a constant to all the values of x, the mean is also shifted by b. So let's add k to x and create a new variable called y. So now let's find the variance of y. That's going to be the variance of x. Now as we said, the variance of x, we just added k to it. So for every value of x, we added k. So x plus k. Now, what about the mean? Now, as we said here, the mean, when we add a constant to it, the mean is also shifted by that constant. So over here, it would be mean minus mean plus k squared. So let's do x plus k minus mean minus k. So as you see, k's cancel. Then it would be e x minus mean squared, and nothing would happen. So the variance of y is equal to the variance of x. And this means that there's no effect on the variance if we add a constant. Now if you go back to the diagram, so this is one distribution. Now let's add a constant to every single value to shift it by k. So this is the mean, this is the mean plus k. As you could see, actual, as we said, the variance is the average distance from the mean. However, when you add a constant, all the values of x move with it. So this would be shifted by k. However, every single value is also shifted by k. So in the end, the average distance squared is the same when you add a constant to it. So that's why adding a constant has no effect on the variance. Now let's multiply every value of x where we add a constant to it. So var to var x, as we said, var x is e. It's the average distance squared from the mean. So if y is equal to 2x, yeah, 2x, let's just say 2 as an example. Now let's start with the graph. Let's call it the diagram way first. So if we take a value here and then we double it, it would be like this. So as you could see, the mean, this is 2mx. So if this is x and this is y, so mean of y is going to be equal to 2 mean of x. Therefore, if you take this point x, then it would be 2x over here. So let's take actual numbers. That would be much simpler. So if we say this is 5 and this is 2, or let's say this is 4, this is 6. Then when we double the mean, when you double every single value of x, now this is 5 is the mean, so 7, 8. So when you double the mean, this is going to be the new mean, so 12. 10, 10, my bad. This is going to be the new distribution. So 4 double it, so it's going to be 8. So 5 double it, and it's going to be 10, and until 12. So this is x, this is y. As you can see, the distance doubled. So if the distance doubled and the variance is proportional to the distance squared, so when you double the distance, then the variance will be doubled and squared, or any constant. If you multiply the distance of x by a constant, then the variance will increase by, will be also multiplied by the constant squared. So I showed you diagrammatically, maybe, no. So with graphs, I proved that adding a constant has no effect on the variance, and when you multiply a constant to x, then the variance is multiplied by that constant squared, because the distance is doubled and the variance is the distance squared from the mean. So now let's do it mathematically. Derivation. So variance of x over here, let's just copy it. So if this is var x, and now we want to find variance of y, so this is going to be e, then ax, as we said, y is going to be, let's say ax now, so ax, and when we multiply every single value by 2, by a, then the mean will also be multiplied by a, so an, and then all that squared. So then we could factorize. So we could common value, okay, a times x minus mean squared, all the squared, and we could put the squared on a as well. So variance of y is going to be equal to this. Now, expect the value of that. Now, as I said before, if you do the math, then you could just move the value of a outside, so a squared times e x minus mean, x minus mean squared. Now what is this? The variance of x. So variance of y is equal to the variance of x times a squared. So if you saw this and got confused, that's why. And of course, as I said, the standard deviation is similar. Yeah, so it measures the degree of scatter of values of x about its mean. So this is the mean. Okay, so it measures the scatter of x across the mean. So it's really similar, but not exactly, because it's the way it's rooted. It's rooted afterwards, not before you hit the sun. So it's similar to the average distance, but it uses the variance. So it just gets the square root of the variance to get something close to the average distance between x and the mean. So cumulative distribution. So basically this means that if you're at this point, you don't want the probability, just the probability of this point, but you want the probability of this point and everything before it. So if you want the probability of the cumulative probability, let's just call that, of x, of everything x and before, then you would just add all the probabilities before. And if for the continuous, you would do continuous distribution, you would do integration. So integration just gets the area underneath the graph. Now, an important part about the cumulative distribution is that it's denoted by big F of x. So if you see f of x, okay, this is the probability of x at that point. But if you see big F, yes, I'm not really sure why they put this. It's probably just to confuse people. But big F means that you're getting the cumulative probability. I see this mistake being done in the homework countless times. So yeah, that's basically everything else. Everything else could be derived. If you understand this part, then everything else would be obvious. So if you were over here, negative infinity, then like there's nothing before it, so the probability is going to be 0. However, in positive infinity, the area would be everything. So that's why it's 1. And of course, the probability is always going to be between 0 and 1. Also, I forgot to mention, so this is cumulative discrete distributions. So it's not going to be a smooth curve, but it's going to be a bunch of discrete values. So 1, 2, 3, 4, and so on. And whenever you get the big F, okay, with cumulative probability, then you're adding every single probability before. So if you're getting this one and before, so if you're getting the big F of 2, then you would add this and everything before it if there were any. So off to negative infinity, there's nothing before it, so it's going to be 0. And to positive infinity, then you would be adding every single probability, so that would be 1. So I hope that would be logical for you. And of course, you could reach infinity to the right, because it will always be 1. Okay, probability generating function. So You don't need to be confused about this. It's just going to be E. So as the same thing about the moment. Okay, so the nth moment is going to be E x to the power r. So everything is in terms of E. So over here, instead of being x to the power r, we just decided inside of E, we want to put t to the power x. And we do this because sometimes it's easier to get the... Okay, so just like the moment generating function, it's called moment, like the first moment and the second moment and so on. It's going to be m to the power r, and this is just e xr. So as you can see, everything is always in terms of e in this chapter. So now instead of putting x to the power r, someone decided we should put e and then t to the power x. Now there are some advantages of this, okay, with because now instead of trying to evaluate e itself, okay, and then like trying to move the contents and whatever, all you need to do is get the derivative. And getting the derivative of this, I think it's quite simple. And also I missed a point over here. So the first moment, as we said, it's just the mean e of x, and the second moment is going to be ex squared. So the probability generating function, so g x of t equal to e tx, which is equal to sum tx times p times f of x. So the only difference here is that you're just taking, so it's normally e of x. So instead of putting x over here, what you're doing is that you're taking t of x and then you're just placing it over here. So as I said, it's easy to get the derivative of it, okay, and then find some extra values, some values that you need. So g of x, and usually you only put t, so they just put t so to differentiate with, but you in probability generating functions you're always going to put t 1 and t as 1. So this is going to be the sum of 1 to the power x times f of x.